Good morning, good afternoon, or good evening, depending on where you are in the world, and welcome to our Pipeline KnowledgeCast webinar. During today's webinar, we'll be discussing how software-defined networking can be leveraged to enable real-time OSS, and we'll feature frontline insight from experts at Deutsche Telekom and Tailf. I'm Jesse Kreiderman, Senior Editor with Pipeline Magazine, and I'll be your moderator today. Now, a couple housekeeping items before we begin. To change your volume for the webcast, just move the slider within the volume area to the left of the presentation window. We encourage you to submit questions for the speakers, and you can do this at any time by typing your question into the Q&A text area to the left of the presentation window, and then just click the Submit button. We'll address as many questions as time permits after our presenters' prepared remarks. If you'd like to download a copy of the slides for today's presentation, you can visit the resource list, which can be accessed by clicking on the green folder icon at the bottom of your screen. By clicking on the other icons at the bottom of your screen, you can learn more about today's presenters, gain access to additional resources, or share your participation in today's event within a number of social media outlets, such as LinkedIn, Twitter, or Facebook. And lastly, if you have any technical problems during the webcast, you can either submit a question or link on the question mark at the bottom of the page below the presentation window, which will take you to the webcast help guide. Well, let's get started. As we reported in Pipeline Magazine, communication service providers are faced with ever-increasing complexity as they work to rapidly deploy network services. Network traffic is growing faster than revenue, innovation cycles are truncated, legacy OSS systems can't cope with next-gen service deployment in a cost-effective manner, and there's intense competitive pressure to rapidly innovate. The traditional way in which network services are deployed requires re-architecting and managing individual network elements. Three new developments have arisen that help service providers address these challenges. The move to all IP network topologies, ETSI's Network Functions Virtualization Standards, or NFV, and software-defined networking, or SDN. So in essence, the power of abstraction has now extended to the network itself, enabling network programming versus individual node management. As evidenced by Deutsche Telekom's Terrestream project, which we're going to learn more about today, service providers can leverage SDN to significantly reduce product innovation cycles and instantly scale and deploy services. This sounds promising, but how can service providers accomplish this evolution, and what kind of results are to be expected? Well, today we have experts from Deutsche Telekom and Tailf with us to answer these questions. Presenting first is Axel Clauberg. Axel is responsible for IP architecture, aggregation, and transport within the group CTO at Deutsche Telekom. Axel has more than 30 years of experience in the IT and telecommunications industry, and most recently, he's driven the Terrestream project, which we're going to be learning about today. After Axel's presentation, we'll hear from Håkan Milroth, CTO and co-founder of Tailf Systems, which provides the software-defined network control system for Deutsche Telekom. Mr. Milroth holds a PhD in computer science and has been at the forefront of software development for many years. So without further ado, it's my pleasure to introduce our first presenter, Axel Clauberg.
Thanks, Jesse. So I will share today how DT's real-time OSS-based SDN approach looks like, and indeed we are using it as part of our Terrestream architecture. So operators globally are in a not really comfortable situation. Traffic is still increasing exponentially. Whether it's a factor of 10 or a factor of 50 until the end of the decade, it really doesn't matter. The problem we're also facing is actually competition. I've tried to symbolize that using a red ocean here. So in the past, the ocean we were sailing in was blue. The sun was shining, and indeed it was profitable business. Today, the ocean turned red. It's filled with blood from competitive fights. So especially in some of the European countries, ARPU has really shrinked to a hardly sustainable level. And we're facing, for example, on fixed line, we're facing competition from cable operators, but we are also facing competition from new players in the market, from over-the-top players who are taking interesting new revenue away from us. And that actually touches an area where operators globally are struggling. And that is our time to market. So as incumbent carriers, we're really good in exploring new technologies. So we were one of the first carriers actually evaluating software-defined networking, OpenFlow in a close cooperation with Stanford. But it actually takes a long time to bring this technology to market and take the benefits of this technology. The reason for that is that we actually carry a lot of complexity, a lot of legacy in our networks. And it's always dangerous working inside a carrier to try and visualize legacy because everyone kind of feels responsible for his part of the legacy. So I try to do something visualizing it with protocols here because protocols seem to be something neutral. So obviously our networks today are IP-based, but in order to drive the IP networks, we are carrying a lot of other protocols with us, and that's including protocols which were highly modern, let's say in the 90s, like ATM or SDH, but they should be gone since many years now, but they're still there. Now, I believe that to actually solve this situation, we need to address three areas. The first one is we need to clean up the legacy. We need to reinvent and simplify IP networks. And really with the main motivation to change our time to market, to simplify and be much faster on the market and be able to drive competition instead of be driven by the competition. So that's what we are driving within the TerraStream architecture, where we drastically simplify the IP network to the extreme that we are only running IP version 6 as a protocol in our network, and all the rest, including IP version 4, is delivered as a service. Now, that was only made possible through an initiative which now became known under the acronym NFV, Network Function Virtualization. We were actually among the initial carriers pushing for that concept, and the whole thing goes back to a discussion I had with Pradip Sen from Verizon during the Open Networking Summit in Santa Clara last year, and another discussion with Don Clark from BT, and we felt actually combining networks tightly with data centers seems to be a good idea. However, doing that, well, it's not just you put everything in the cloud and you're done, but it actually requires a lot of changes in the architecture of the applications we're running today, but it also requires changes on the vendor side, because vendors today are very profitable selling hardware appliances to us. We want to move them to a software-based model, moving kind of to virtual appliances. And we felt we actually need an operator forum to push for that, because without that push, it's just not going to happen. So this is the second element for us in accelerating and being more flexible, and it is a real important element there. And I see this equally important as the third one here, and that's software-defined networking. Because a lot of the problems we're actually facing today with a long lead time for mass market products are down to the operation support system we're using to control our networks today. Typically, services are hard-coded in the OSS today, and here it seems that software-defined networking overall brings a solution. Now, I'm also representing DT in the board of the Open Networking Foundation, and as SDN is such a hype, I thought it would be good to just explain what SDN actually is. And I'm using two slides which originate with the Open Networking Foundation here. So the concept of SDN, I think it's most easily explained if you think some years back on the computing side, we had mainframe computers, and today we're in web-based computing or cloud computing. And the old mainframes, well, they're still there in some niche markets, but they have largely been replaced. Now, in networking, we still have mainframes, and those mainframes are called Juniper PTX or Cisco CRS or Alcatel-Lucent 7950 or Huawei NE40. Now, is there still a reason for living for those mainframes? Or should we move to a model where we actually have very simple standard hardware out in the field, distributed traffic forwarders? We would add a central controller, and that would just have an easy way of putting network applications on top. So that was the original idea behind software-defined networking. Separate control and forwarding, and then through central control, enable the deployment of applications much easier. Another view, looking also at the protocols which are typically needed here to actually make that picture happen. Those protocols are standardized by the Open Networking Foundation, and here we have the OpenFlow protocol, which is actually used to talk from the controller to the networking devices. Well, does this way of thinking SDN actually solve our problem? Because if you look at the picture here in detail, the controller has to talk to the device, and here we are using a new protocol, the OpenFlow protocol. We have a 60 billion euro business running on top of basically IP today. So what's the risk actually moving to a new control protocol? We still need IP. Actually, the controller still needs IP to talk to our devices. So I'm not sure actually whether this completely solves the problem and whether this is actually the problem we want to address. Because we don't want to program the network. We want to shorten our time to market. So our business is actually delivering services. So we want to program services instead of re-architecting the network and the management system for every new service. And that's actually a sentence my friend Peter Lofberg once said during the development of TerraStream, kind of creating the vision how our real-time OSS SDN approach would look like moving forward. And I think this is really key to understand. What do we want to do with software-defined networking? And I believe for carriers, the answer is not that we program down to the TCAM level and influence individual flows in our network. We should focus on services instead. Now, you're going to hear more on this slide from Hakan following in the second presentation here. But we're brave enough to say that our new networking vision and new architecture, TerraStream, which we have deployed in December last year in a pilot in one of our affiliates in Croatia, that TerraStream is actually DT's first software-defined network. The big change we're moving to here is actually the way we model the network, the way we model services. So in our existing OSS, which is still in production today, services are actually hard-coded in the OSS. And that's a very non-scalable model because you have to change a lot of the IT systems actually to roll out new services. Also, there is kind of a dependency on vendors because typically we are accessing the networking equipment through element managers. So the existing OSS has to know about the element manager and its capabilities to access the network. We thought there should be a different model. In fact, there are standard schema language which have been standardized in the IETF, for example, like Yang, which is RFC 6020. And there are standard protocols like netconf, XML-based protocols, also standardized in the IETF under RFC 6241. Couldn't we use such a model, actually, standard data models to describe, for example, a router, a switch in the network, and then use netconf to access the router, to access the switch from the OSS, a standard way of accessing the device. And actually, if you model the network in a high-level language, Yang, you can use the high-level language as well to model services. So you can describe a layer 2 or layer 3 VPN service or even a retail customer connection just based in Yang. And then you can map it to the network. And if you combine this with real-time planning and some other components, you have what we call the real-time OSS. And actually, such a concept is very flexible because you can also, for example, insert an OpenFlow controller in the picture here, which is shown on the right side of the slide as a future extension, or you can use the netconf and Yang way of accessing devices, which is basically also the configuration protocol as part of the Open Networking Foundation OpenFlow world looks like. Now, while we believe in this concept, I believe carriers have to go through massive changes actually to make that reality. These are changes which are impacting people and skills. I believe we need new skill set combinations in carriers, in operators overall. That's a combination of IP, data center, programming, and operational skills. And it's pretty much like what the internet companies are using today, what the Googles, the Facebooks are using in their team today. And we on the operator side will move to similar skill set combinations. But this move to more a software-defined operator is actually also implying changes on the processes side. So the old waterfall processes have to change. We have to move to agile processes. And the time of the large teams with hundreds of people working on a project, I think it's basically over. We see more the small empowered teams who are able to make decisions and really also take the responsibility from the original architecture blueprint until deployment. We also see a need actually to focus on standards. And I just show the ITF part of the world here. And I mentioned this young data model we can use to access routers and switches. The problem is that this young data model doesn't exist as a standard yet. In fact, vendors were trying to prevent this from happening because, sure, they got the point. If I move to a standard young data model describing a router, it doesn't really matter whether I have Cisco, Juniper, Alu, Huawei, Ericsson, whoever. They would be replaceable. And so there was not a lot of consensus from the vendor side in the ITF to actually support such a model. And we're just now reaching a point where there is enough momentum that we can change this also in standardization. And this is kind of laying the foundation for the future. And Hakan is going to step more into this over the next slides. So with that, let me hand it over to you, Hakan.
Thank you, Axel. So I would like to start with a 1-minute summary of Tailf, since we are a bit smaller company than DT. So basically, we've been around since 2005. We have about 85 customers worldwide. We are based in Stockholm, but also have a U.S. operation. We are a software product company, which is an important distinction. We focus on products rather than professional services. And the products we produce aim at centralized network control and making network automation possible. And we market this software into 3 markets. Service providers like Deutsche Telekom, data center operators can be service providers, but can also be pure play data centers or enterprise data centers. And we also sell our software to the network equipment vendors. That was actually our initial market. And you see some of our largest customers here on the screen. So our product is called the Network Control System, NCS. That's a very generic name for a product, of course. But what it is it's a multi-vendor, service-oriented SDN controller. And I will go through what I mean with both multi-vendor and service-oriented in later slides here. So on top, so north of NCS is the realm of the management applications. In telecom environments, it's the OSS and BSS systems. It can also be in a data center, cloud orchestration systems. It can be workflow engines, policy control systems, all kinds of management applications. And south of NCS is a network. Let's take a look at what assumptions we make about the network here. For this, we don't make any assumptions about what network we are controlling really here. It can be a layer 2 network, layer 3, layer 4 to 7. It can be traditional hardware-based network devices. Increasingly, we see virtual network appliances, NFV style, as Axel talked about. And it can also be more experimental kind of networking applications and devices, such as those made possible by the OpenFlow standard. And the way to access that sort of heterogeneous network is preferably using modern protocols like netconf, but in reality, the installed base for many of our customers is that the only way you can actually program those devices from a central point is through a command line interface, most commonly. Can also be through SNMP or SOAP or a REST interface. So we sort of try to work with whatever is available from the network devices and program the network that way. Before going into more details about what NCS does, I want to go through a couple of use cases from actual customer deployments to give you a feeling for what we can do. What is the sort of range of problems that we can solve with this technology? The first use case is actually managed services for enterprise customers, and that's a big business for many telecom service providers to sell managed security services. They traditionally sell connectivity services and VPNs and business services, and now many also see a possibility to sell layer 4 to 7 security services as managed services to their enterprise customer base. And we are working with a large operator in Asia in deploying this. And this is a combination of NFV-style WAN accelerators and routers at the customer branches and security service chains at centrally located data centers. And this also has a component of managing an open flow switch, because layer 4 to 7 service chaining, as you see here, is one of the best examples that I have seen of a real-life application of open flow to steer a packet through. It should go through the firewall, it should go through the intrusion detection, etc., on a per flow basis. But when you do that, you also need to be able to reconfigure the firewall, regardless of whether it's a Palo Alto firewall or an F5 firewall or whatever it is. So you need to have this combination of controlling open flow switches and controlling third-party security appliances. And you need to be able to do this at scale. So here we are talking about tens of thousands of tenants in each data center. So that's one use case of our NCS technology. Next use case is actually mobile transport networks or mobile backhaul networks. This is a picture from one of our partners, Nokia Siemens Networks, that we published a partnership last fall. And here the problem is really the IPification of the mobile transport network. There is a lot of tunnels being provisioned very dynamically in a modern LTE network. It can be MPLS tunnels, it can be Metro Ethernet E-lines, it can be IPsec tunnels, it's often tunnels within tunnels within tunnels, and it's a very complex provisioning exercise. And this is something that clearly is now becoming non-sustainable to do in a manual way. You need to have programmatic support for doing this much more rapidly than using traditional CLI-based approaches. Okay, so if we look at another use case of the same technology, this is a pure data center deployment, and this we actually have a series of customers that fit this exact description. Before picture is on the left-hand side here, and the after picture is on the right-hand side. And their problem is not really the problem that Axel described as typical for communication service providers. Their problem is more scaling their operations. And there, the network engineers with their manual processes is a bottleneck. So to be able to scale to bigger data centers and to roll out new data centers, they need to go from a situation where they have network engineers logging into individual boxes, maybe having ad hoc scripts that are specific for particular vendors, especially in the layer 4 to 7 space. So they have specific F5 scripts, specific scripts for this firewall, that firewall, etc. And instead going to the right-hand side of this picture, where you put in an abstraction layer to the network, where you sort of hide the complexity and the diversity from different vendor interfaces to both the network engineers and to network automation applications running on top of this network abstraction layer. Okay, so that gives you sort of a background on how our customers use NCS. And if we look at what does it do really as a technology, well, it has, I would say, 4 key features. First of all, the whole architecture is model-driven, and this was exactly what Axel was talking about. This gives the flexibility to model your network services, but also model the elements, the network elements and the devices in the network. Model that instead of hard coding that into some software application. If we have a declarative data model describing the services and declarative data models describing the network devices, then we have much higher chances of having a very agile and flexible system. Okay, so that's the first important feature set. The second one is transactional guarantees. I'll talk more about that later. And the third key feature here is being able to map high-level services, the things that have SLAs, the things that Axel is selling to his customer base, VPNs, retail services, etc. Map that into the actual configuration elements on the various devices throughout the network. That's a big gap in abstraction level between the services and the actual configuration state in the network. And that is something that a product like NCS needs to be able to bridge that gap and do this mapping. And finally, we also need to be able to read performance information from devices and map that into service APIs. Because you can think of an SDN system as a closed feedback loop, where you read performance information, analyze it, and then dynamically reconfigure the network accordingly, so you maximize the utilization of the resources you have in the network. So being able to read performance information and map that into service level performance indicators is also key. Okay, so what I will do now is go through these 4 features one by one. The first one, model-driven architecture. We have talked about the importance of that, both Axel and I here, and I think this is the absolutely single most important thing in a modern real-time OSS system based on SDN principles. You need to be able to model both network services and network devices in declarative data models and not hard code that into either the network elements or the OSS or any SDN controller for that matter. You see many SDN controllers today where you have very hard-coded assumptions about what is a network service and what is a network device. That doesn't give you the flexibility that we want here. And we use, in our NCS product, we use these data models, the Yang data models for the services and the devices. We use that as the basis for everything. It is the schema for our embedded database where we store all information. That is in Yang. The Yang models is the schema for the database. There is no translation into an SQL schema language or something like that. We have a native Yang database as the heart of the product. And we also auto-render web interfaces and other human-machine interfaces for network engineers from those data models. And all APIs are Yang model aware, which greatly simplifies the task of writing automation applications, the OSS applications on top of NCS. It's a programming model that is very similar to a web programming model where you navigate a DOM tree. Here you don't navigate a DOM tree, you navigate a Yang data model or a set of Yang data models for the services and for the devices in the network. But the programming techniques are similar to the web world. And we can also use the data models to automatically derive the right command sequences, whether it's netconf, CLI, SNMP, SOAP, REST, whatever. We can generate automatically those command sequences, push it out to the network, and this is driven by the data models. So data models are key here. Okay, if we look at transactional guarantees, we have to realize here that what a management application really does here is writing information to the network. That's one of the key tasks of an OSS system in a terrestrial scenario, for example. And that means being able to create a service instance, update the service instance, and delete the service instance. And whenever you do these kind of high-level service operations, you change a lot of things in the network. And the network is a distributed system. The SDN controller, the NCS piece here in this diagram, that's not a distributed system. That's a traditional centralized system from a programmer's point of view. But the network is distributed. And whenever you write information or do changes to a distributed system, the really tricky part that is always coming back as a big problem is what do we do if we have failures when we do push out changes to a network? And a typical example here would be we add a leg to a VPN to connect the new branch office. That's a simple operation to do at the service layer. But at the network layer, that might require us to actually reconfigure several, say, 5 different provider edge routers with non-trivial configuration changes. And what happens if after we have reconfigured 3 of them, when we are reconfiguring the 4th one, we have a failure due to, for example, some resources like memory is constrained, can't push through a change. How do we back out to a well-defined state, the state we were in before we did this provision, this new service change? And that is a classical distributed systems problem, really. And the distributed systems world, especially the database world, has been dealing successfully with this problem for more than 30 years. And the abstraction, the technique they have used is distributed atomic transactions. So that is what we are doing as well. We implement all changes at the service level. When we map it into changes at the network layer, we deploy those changes with transactional guarantees. We implement a distributed two-phase commit protocol through the network so we can give transactional guarantees. And you can think of transactional guarantees as the operation is atomic. It either succeeds in its entirety or nothing. If it fails, nothing changes. So you never end up in a situation where you have a non-defined state. So transactions is just the fancy name for atomic change sets. And what that gives us, if we can guarantee with transactional integrity here that all changes are either completely effective in the network or nothing changes at all, it actually gives us the capability to have a 100% correct, up-to-date, real-time view of the network state in NCS, in our embedded database. Of course, that also requires us to be able to handle situations where someone sneaks in and log in directly to, say, a router and do some change, either a crucial, necessary change or doing something foolish on one of those devices. We need to be able to very efficiently check sync operation. Checking is our view of the world in sync with the actual network, and if not, we need to be able to display to the network operator here what is the diff set, meaning that device number 17 differs from the database in the following way. Mr. Operator, what do you want to do about it? Do you want to override the device, or do you want to import the diff from the device into the database? That's something that typically needs to have a human in the loop. But that's the kind of real-time capabilities that is possible if you can have transactional guarantees in the system. Okay, we go to the next key feature of NCS. It's something that I alluded to earlier, that the operations from the management applications, be it OSS systems or cloud orchestration systems or other kind of management applications, is basically service lifecycle operations. Create a service instance. For example, create an Ethernet E-line between A and B for a customer, or create a virtual network for a tenant in a data center. And it's also update operations, like add a leg to this VPN, or bump up the quality of service guarantees for this particular point-to-point virtual connection. And it's delete operations, being able to decommission service instances. And when we do that, we of course also want to clean up the resources used in the network by that service instance. So for example, if we have can take the simple example of a virtual connection that we delete. If the resources used in the network by that virtual connection is not used by any other service instance, we should actually remove those config elements from the network. Otherwise, we, after a while, will end up with a lot of orphaned configuration elements in the network that no one knows if they are in use or not. So effectively, we want to do garbage collection at the network layer here, which is something we do implement. Okay, so this diagram here illustrates how we map these kind of high-level operations into device-specific command sequences using whatever protocols is available from the network. And we do that in two steps to reduce the complexity of it. First, we map the service operation, like add a leg to a VPN or create an E-line, whatever. We map that to the corresponding configuration changes in the network, but at an abstract layer, as we represent the network within as a Yang data structure in NCS. So it's a simple Yang data to Yang data transformation, which greatly reduces the complexity of this task. And then from that step, we can then, as a next step, generate the specific command sequences that are specific for various equipment here. So that's one of the simplifications we do in this mapping layer. And equally, or probably even more important simplification we do in this mapping task is that I mentioned that we need to be able to specify how to create a service instance, but also how to update and delete a service instance. We actually have a technology where it's enough to specify how to create the service instance, and then our system automatically generates the methods for updating that service instance and deleting that service instance. You don't, as a user, have to tell the system how to do that. You just tell the system how to create the service instance. And you don't have to worry about error recovery, because this is all happening within the scope of a transaction. So we have reduced the problem of mapping high-level service operations to the things that actually happens in the network. We have reduced that probably by 2 orders of magnitude. To give some examples, some numbers here, we have done implemented a wide variety of business services and also some consumer services with this technology, and a reasonably realistic implementation of some VPN services is between 1 and 200 lines of declarative service definitions and about 100 lines of declarative template codes that describe the mapping from service instances to changes in the network. And that is probably 2 orders of magnitude less than I've seen in any other similar system. So I think we have made some significant contribution into how easy it is to implement the service, and that's what it all is about, as Axel was talking about. How do we implement services? So it's easy to implement them in the first place, but also easy to add features to them as they evolve over time. That's what we're shooting for here. Okay, I won't say much about. Well, here, before going into the operational data, it's worth mentioning that there are actually 2 life cycles when we talk about services. I just talked about the life cycle of a service instance. For example, the life cycle of a particular VPN for customer X. Of course, there is also the life cycle of the VPN service itself, the definition of it. So you want to be able to define in Yang service, but then you also want to have support for the whole life cycle where you add features to it, that is, extend the Yang model, being able to load it into a running system without disturbing the system. That is an in-service upgrade of the service definition. And you for sure would also have the requirement that you can run multiple revisions of the same service simultaneously in the same system. Because for customer X, you might be running revision 1.1. For customer Y, you might run revision 1.2 of your VPN service. And this should be supported within the same system, and it should be possible to add those features without disturbing the operations. So that's important, of course, as well. Okay, finally here, I touched upon this topic initially, that we need to be able to collect device performance data and other kinds of operational data, and and represent it in a unified format, regardless of how we collect it, whether it's over SNMP or CLI or some other method. We want to have it represented in our network control system in a normalized way. And that is taken care of by the Yang data model that also allows us to specify the operational data in the Yang models. And then we need to be able to map that into service key performance indicators that we can then communicate to some dedicated performance management system or a traffic planning tool or some other kind of analytics engine that can make use of that information. So I think that was basically a quick run through of the capabilities of our network control system. And hand it over to you, Jesse.
Thank you, Håkan. We're now ready to open the floor for questions from the audience. As a reminder, to participate in our Q&A, just type your question in the Q&A text area and click the Submit button. Now, I did see someone already asking about today's slides. Just a reminder, you can visit the resource list by clicking on the green folder icon at the bottom of the screen to get the slides for today's presentation. Our first question here, Axel, why is Yang to be more successful in vendor adoption than something like a TMF frameworks?
Well, it's sure a subjective answer here, but I believe we're seeing the value here of an open internet standard developed in a very open process in the IETF. Sure, we have to admit it took a couple of years before it is finally taking off, and we're just reaching this point in time now that Yang is taking off. But when you look at, for example, Open Daylight or activities also within the ONF with OF config, there you see it's finally being adopted widely, and we see actually a large trend in there right now.
Okay, so you do see that trend there. Interesting, very interesting. Is there enough support for open solutions in the NEM community to enable the evolution of SDN to the extent that we're kind of talking about today?
Well, I would say it's a related question. So it took some time until the large network element vendors actually jumped on. With my board role in ONF, we had a few committed contributors to ONF, but just over the last year, I would say SDN converted from a hype to reality. So we see broad adoption in the vendor landscape now.
So yeah, I do see the broad adoption occurring. Okay. Okay. So another question I have here for that's actually been asked a couple times is now that we have the advent of programmable network elements and abstraction, that's kind of what we've been talking about today. Is that changing the culture of the CSP? In other words, are service provider organizations trending towards more IT organizations, less engineering, and maybe how this evolution is changing the nature of the business?
Well, I guess that's for me as well as someone working for a service provider. I would say, first of all, the problem we are working on here is not a standard enterprise IT problem. So that's very important to understand that it's a little bit different from standard enterprise virtualization projects, what we are driving here, both with our SDN approach as well as with our infrastructure cloud approach. Now, having said that, indeed we see a big change in the ways we are putting teams together, because we basically need that mix of networking skills, operational skills, data center skills, but also programming skills. So when you look at some of the internet companies, that's exactly the mix they actually have in their teams, and that's something also the operators will have to adopt.
They're going to have to adopt it as well, sure, for sure.
Yeah, that doesn't mean that it's less engineering, it's just a different combination.
A different mix, yeah, sure.
Yeah.
Håkan, here's a question for you. Could you describe how NCS's Yang models would evolve when standards are established, but then also while maintaining backwards compatibility?
Yes. So the Yang RFC 6020 has some very strict and well-defined rules how you can update a Yang data model and still maintain backwards compatibility. So there are certain operations that you can do while updating that data model and stepping up the revision of that data model. And if you go outside what is allowed to do, then you basically need to branch off that data model into another data model if you go outside those rules. But in typical cases, if you're aware of the rules that the Yang standard mandates for maintaining backwards compatibility, you can stick within them. So there is a built-in mechanism for the life cycle of a Yang data model in the actual standard itself.
Okay, so it's in the standard itself. Interesting. Jumping off from there, I have another question here for you, Håkan. So if a transaction initiated from NCS is to program multiple network devices and one of them failed, then are you roll back all the device configuration that already went through?
Yes. So we roll back that to the initial state before any changes were pushed out to the network. Mm-hmm. And if the devices support a proper implementation of netconf, that's reasonably easy to do. It's much harder to do if the way to program or changing the devices is through, for example, a traditional Cisco-style CLI. Then it requires some pretty clever algorithms to be able to do that. But that's exactly what we do. So we can guarantee that if there is a failure somewhere when you change multiple devices, we automatically roll back to the initial state.
Okay, so it just rolls back. Excellent. I don't know, Håkan or Axel, which one of you want to take this, but who produces the service models? Tailf, the CSP? Is there a library that already exists? Does NCS have a built-in library?
I can answer it from a Tailf point of view. We have a library of sort of boilerplate versions of the services that we have encountered among customers. But in reality, especially for communication service providers, no two CSPs have exactly the same definition of a given service. So everyone implements VPNs slightly differently. So what we do is we provide a starting point, and then typically the service provider adapts and changes that to their particular likings. And that's a great benefit of having an open model here. That it's like open source, but here it's open models. You can actually, as a customer, change the data models and thereby changing the definition of your services. So you don't have to rely on some vendor to do those changes.
So it's more open.
Let me add there. If you're looking at the network element layer here, that's an area where it's indeed important for us to work together in the Internet Engineering Task Force to define those models. And that's sure a non-trivial task. As mentioned, the vendors are were for a long time not really in favor of that approach, because getting rid of element managers means the vendors are more or less getting more replaceable in our networks. But we even see that changing now. So we see the first signs, even from the very large vendors, that they are willing to change this. And I'm very confident that we're going to see a lot of open standards also in the data model area around our network elements.
That's really interesting. We've been covering that open standards. Very, very interested from pipeline point of view as well. So how does NCS differ? This is for you, Håkan. How does NCS differ from traditional multi-vendor EMS, NMS to manage a multi-vendor network?
Yes. So the difference, I mean, there are many differences, but typically a traditional NMS is first of all focusing mostly on the read part of reading information from the network, be that events or alarms or performance data. Not so much writing information to the network, especially not in real time. So the place in a traditional BSS OSS stack where NCS fits is right below the order manager. And so we take the output from an order manager and make that happen in the network. So that's our role here.
So it happens right in the network. Interesting. Is there any process to make sure the network changes or test before pushing to the live network?
Yes, so we absolutely, and that's very important. So we have when you commit, or rather when you are about to update the network with some change, say you changed your service in some way. Okay, so that means you are committing that to the network. But we also provide a commit dry run operation here, so you basically can do a what-if analysis. So if I go through with these changes, what exactly will happen on my Cisco routers? What will happen on my firewalls, etc.? And you can, and the network engineer can then look at that, say, okay, looks good. I think that works, and it then commits for real. And that's we have learned that this is a great way to sort of earn the trust of the network engineers operating this, because they want to have full transparency into exactly how are the devices in the network changed. Otherwise, they don't trust the system.
Right, yeah, the testing is important. This question is for Axel, and maybe it was semi-answered earlier, but by when do you foresee that real-time OSS-based SDN is ready for commercial deployment at DT? If you could answer that for us.
Well, we're currently in the pilot phase in Hradski Telecom in Croatia, serving a couple of 100 customers right now. And we always worked on a multi-year plan. I think the full concept of the real-time OSS, and there are many areas which we actually have not covered here today, touching, for example, real-time planning and other aspects. That's I would say 2 to 3 year activity for us. But by the end of the year, we want to be ready with a full proof of concept quality implementation of all our concepts.
Yeah, that makes sense. So maybe you can answer this question as well, Axel. How is geographical redundancy achieved when using NCS in an SDN approach? And I guess this is specifically in relation to provisioning information during a failure.
Well, we are building a distributed and redundant database for all our networking data underneath. So this is an important part we have not touched today. Now, in general, when you look at NCS, like any other service, the geo-redundancy is something you can achieve with distributed data center concepts and optimization together on the IP layer. So for our generic services, for example, we're using a lot of IPv6 Anycast to make sure we have geo-redundant, high available services. But on the NCS-related part, I better leave that part to Håkan.
Yeah, so basically we replicate in real time the contents of our database into multiple data centers. Okay. And then we typically also, and in testing we do build a hierarchy of these NCS systems. So you can closer to the edge, you can have sort of local, you can view them as caches, read-only caches, and then at more centralized places you can have read-write access to those databases. And another distinction we make in that hierarchy is that we, in the distributed layer of of the database, we store the configuration state of the devices in the network, whereas the state of the services are typically stored in fewer places higher up in the hierarchy. And that builds availability.
Yeah, that makes sense. How does SDN handle OS updates, keep alive messages, routing updates, that sort of thing?
Well, SDN by itself, probably not. The way we have implemented our SDN model here in Terrestream, we have not touched the IP control plane. So we're still running a standard ISAS, we're still running a standard BGP, because we know that is absolutely scalable and delivering according to our needs. So if we're looking into other SDN models like the OpenFlow-based SDN model in a data center, you can easily handle that. In the wide area, there's still some challenges we're currently working on as part of the ONF work. So I would say the impact here is rather limited on these topics.
Does the standard cover some sort of MIB API discovery that allows for some automation of the services, flows, and rules?
Hakan, you want to take it?
Yeah, I didn't really understand that question, actually.
Me neither, that's why I pointed to you. No, but seriously, I think the way services are interconnected, that's still up for work. So the current standards don't touch that part in detail yet.
Okay, that makes sense. Have there been any performance studies on the real-time behavior of NCS as a function of service complexity and the underlying hardware needed for the level of transactional computations? Any performance studies?
Yeah. Oh yes, we have lots of performance studies and measurements, and well, first of all, the basis for NCS performance is that our database is an in-memory database, and today memory is cheap, and you can load lots of RAM into a server. So we run, for example, the full configurations of tens of thousands of provider edge routers in a single instance of NCS as part of our regular revision performance tests. And that requires less than 32 gig of RAM in a server. And today you can buy a server with 32 gig of RAM for a few $1,000s. So being able to store that in RAM is key. And nowadays, with 64-bit architectures, you can actually run quite large installments from a single server.
Several folks in the audience today are asking about the definition of real-time OSS. One question asked about, are we talking milliseconds, seconds? And maybe we could just wrap a little definition around that today. What is meant by real-time, I guess?
Yeah, well, we are dimensioning our system so we can process roughly one transaction per customer per second. So you can compare it to maybe an autopilot for a plane. So typically when planes are under autopilot, they don't crash, and that's the similar intention we have for the network with our real-time OSS.
Excellent. Yeah. Okay. Make that,
Another way to answer that is that in traditional OSSs, they are anything but real-time, and the reason for that is basically that they store the information about the network in an inventory system that is effectively not an online system, that is not updated in real time when you do changes in the network. Right? So that's the big differentiator here, is that we keep the network config state in a real-time database rather than in an inventory system. And we let the inventory system be an inventory system, meaning that that's where we keep information about assets, basically, and not the actual config state in the network.
Yeah, that's a marked difference for sure. Hakan, this is kind of an interesting question. Will public-private cloud have anything to do with this?
Yes, absolutely. I mean, that's both public and private clouds. The intersection between what we talked about here and private public clouds is basically how do you separate? Well, how do you get the VPN connected to the concept of a tenant in a data center? And that's for sure an important aspect of any systems like this to be able to handle that problem.
Thanks, Hakan. I have one more question for you, Hakan, here. Do you see a common model like Yang is critical to this SDN success? In other words, yes, you can go ahead.
Yes, absolutely. I think converging on a common, good enough data modeling language for both the network layer and the service layer. And when we talk about services here, I primarily mean what the TM Forum call resource-facing services. Converging on a standard language for that is key to making progress in this area.
Yeah. Well, we've reached the end of our time. We have a flood of questions. Our presenters will be able to address some of these unanswered questions by email, but I'm sad to say we have reached the end of our time today. On behalf of Pipeline Magazine, I'd like to thank Axel Klauberg from Deutsche Telekom, Hakan Maroth from Tailf for sharing their valuable insights, and I'd like to thank all the attendees all over the world for their time and participation in today's KnowledgeCast webinar. Have a great day, everyone.